Hello everyone. My name is Yasmin Farzan, and I'm a chemical engineering junior at Virginia Tech. I do undergraduate research on synthesizing an oxygen-based ligand for supporting iron complexes for carbon-hydrogen activation catalysis, and today I'm gonna tell you about it. So let's start by why cleavage of carbon-hydrogen bonds is essential. Well, that's a relatively simple question. In order to convert common hydrocarbons into more useful compounds, we have to do that. And we currently use petroleum, oil, and natural gas to synthesize lots of our common commodity chemicals and also use as energy production resources. And to enable such transformations from common hydrocarbons into these resources, we have to break carbon-hydrogen bonds from long carbon chains. For example, converting natural gas into methanol, replacing a carbon-hydrogen bond with a carbon-oxygen bond, would allow us to use a liquid, methanol, instead of a gas, which is a lot easier to handle and also more environmentally friendly for energy production. So where is this process used? It's actually used in lots of industries, such as gasoline, clothing, and pharma industries. And these companies rely on common methods to cleave carbon-hydrogen bonds. But the byproduct of these reactions, the low selectivity of the products, and the necessary conditions, such as high temperatures, are very costly and not environmentally friendly. So in my research, we try to find better ways. But what makes this process difficult? Well, it is that carbon and hydrogen have very similar electronegativity, making the bond very stable. And that means they are kind of inert in nature, and they don't want to react with anything. This means that companies have to put in a lot of energy or use expensive metals such as platinum, palladium, or rhodium to break the bond. This process it works, but is not sustainable in the long term. So in my lab, we borrow inspiration from nature to convert common hydrocarbons into more useful compounds. And, oh, I forgot to click this. So our inspiration is methane monooxygenase enzymes, which you see on the left side. And this enzyme basically converts methane, which is a very substrate to activate, and it does it at ambient temperature and pressure using oxygen gas as the oxidant. And we seek to develop similar ligands that will have similar properties to this enzyme to enable us to support stable yet highly reactive metal complexes. So our current procedure uses published methods, and we have made the ligand on the left side, and reacting it with iron metalling reagent, we've been able to insert the iron into our ligand to coordinate the oxygen groups. And as these complexes are very air sensitive, we have to carry all these reactions with a nitrogen-filled glove box, so everything is done in that. The structure of the iron complex was obtained using X-ray diffraction and also NMR. And the X-ray diffraction showed the connectivity of the iron with oxygen, and the NMR further confirmed that using the peaks in literature. So the diiron complex was formed, and I'd like to note that the NMR spectrum extends more than just 0 to 15, which is typical for organic compounds. But since we have unpaired electrons, it goes to the paramagnetic region, and we have peaks from -5 to around 45 ppm. So since we are interested in the oxidative chemistry of this iron complex and its ability to promote carbon-hydrogen bond cleavage, we wanted to use oxidants. But oxygen gas is kind of hard to handle, especially in the glove box, so we used azides as analogous to oxygen. And upon reaction with the metal complex, azides will result in a metal center bonded to a nitrogen R group unit, whereas the dioxygen would give a metal oxygen bond. And the oxygen and the nitrogen R group have the same number of valence electrons, so they behave very similarly. Okay, so we initially started with adamantyl azide and proposed the following two products would be formed upon addition of the azide to the centers. And upon crystallization, we identified a diiron-bridged oxo, or O2 negative, with adamantyl anilus substituents, as shown in the crystal structure on the right side. And we believe that this product is likely the result of decomposition during crystallization, likely upon reaction of the initially formed species with trace water. And we also followed the reaction with NMR to gain further information. The stacked NMR on the left side illustrates that new peaks, which help us identify new products or different products, are formed right after the adamantyl azide is added to our metal complex. And over time, these peaks grow more intense, suggesting that the reaction is not instantaneous. So the peaks on the NMR and the peaks that correspond to the crystal structure on the right side do not match, which suggests that the target iron emitter was likely generated in the reaction and then rapidly reacted further to form the adamantyl aniline. And we believe that through careful manipulation of the reaction condition, the iron complex may be directed to afford carbon-hydrogen cleavage. And we also wanted to test our product on different substrates. And we started with styrene, the monomer for polystyrene. And we chose this substrate initially because styrene is easy to activate compared to lots of other substrates. And we used 5 equivalent of adamantyl azide for this reaction, and we ran the reaction at room temperature and also at 60 degrees Celsius. And we analyzed the product using, again, NMR, and the peaks on the NMR suggested that the aziridine product was detected. So the last carbon-hydrogen bond was actually replaced with the NR group that we talked about earlier. However, the yield for this product was very low, and this made us want to try a different reaction with another azide that might be more reactive. So the next azide that we tried was bis-trifluoromethylphenyl azide, and this reaction ran at room temperature overnight. And the yield for this reaction was higher than adamantyl azide, and we got a yield of a bit higher than 30%. And to see how much yield we got, we used the standard ferrocene, and given a known amount, we were able to integrate the corresponding peaks on the NMR and back calculate the amount of product formed. And the ferrocene is not shown, but we used it. In conclusion, we are interested in designing oxygen-based ligands used to support Earth-abundant transition metals that could serve as catalysts for carbon-hydrogen bond cleavage. And our future focus would be testing our products with different azides, analyzing the role of substituents, and finding the proper reaction conditions, such as temperature, stoichiometry, and reaction time. Yeah, and I'd like to thank the IONS group at Virginia Tech and the funds that Virginia Tech gives me, and the Department of Chemical Engineering and Chemistry and AIChE for making this possible. Thank you.
All right, thank you very much. So I got a little confused. So you're taking the di-iron catalyst and some hydrocarbon and reacting it with this amine and so nitrogen gas will come off or something?
No, the
You have
nitrogen.
to
We are
filter it.
using a nitrogen-filled glove box.
Mm-hmm.
So when we are running the reaction, sometimes even the pressure is at one pressure, but it's using nitrogen gas instead of air,
Mm-hmm.
because we don't want oxygen to react with any of our compounds, which are very air sensitive.
Okay. So do you guys have any ideas about the mechanism by which the catalyst is doing this reaction?
Yes, we do. It's not shown in here, but basically the iron complex and our ligand react together, and then the azide would react at the end to be added to our substrate.
Okay. Oh, you have a question? Okay. Just one more question, I guess. So are both of the iron sites participating in this reaction then? Is that what
Yes,
Yeah,
that's
okay.
why we're using,
Okay, just wanted to
Yeah, it's
clarify.
one-to-one,
All
ratio.
right, thank you.
I guess just a general thing. You said you're inspired by how enzymes do this job, right? So how what you're doing is similar to that? Could you?
Yes, so let me get back to the structure. So this is the methane monooxygenase enzyme, and we've been inspired by the structure of it on the left side. So as you see, it has two irons connected to oxygens, and that's why our proposed ligand on the right side basically follows a similar structure to that enzyme. Thank you. All right, thank you.